Hey, let's take a look at the section 3.5 notes, limits at infinity. So we've spent time talking about limits in chapter 1, but always we're moving towards a finite number, like x was 7 or -1 or something. But sometimes we want to know what happens to the graph as we move farther and farther away from the origin. And so we would say what happens as we approach infinity. So let's take a look at this first example here. So we've got f of x equals 3x squared over x squared plus 1. So some of the things that we might look for with rational functions in order to plot them might be their y-intercept, their x-intercept, whether they have any vertical asymptotes. So if we look at this, in terms of vertical asymptotes, we don't get a whole lot of information because x squared plus 1 only has imaginary roots, so there's nothing there. If we put in 0 for x, that gives us 0 for y. And so that tells us that the origin is both the x and the y-intercept. Again, it would be nice if we got some x-intercepts and some y-intercepts, and a y-intercept, but now we just get one that does the job. So instead of just maybe starting to make a table or something, let's just talk about symmetry first. Just because, again, that also gives us some clues as to what the graph looks like. And so remember, we had two kinds of symmetries when we knew it was a function, and one was y-axis symmetry, and the other was origin symmetry. This goes all the way back to chapter P, our review at the beginning of the year. And so for both of them, we're going to plug negative x in, and we want to see what happens. Right? So with y-axis symmetry, again, that would be something like a parabola where there's the y-axis goes through and acts like the mirror there, reflecting the one side over the other. So if we have y-axis symmetry, then what should happen is if it won't matter if we put in negative x or x, we should get the same thing back, right? So if we plug in negative x and we get the original function back, then it's got y-axis symmetry, sometimes called even. And then if we plug negative x in origin symmetry, again, what that means is that in the first and third quadrant, everything just kind of mirrors through this point. So if I pick an x value here and get a y, then if I pick the opposite x value, the negative version, then I also get negative y. So what this looks like is I put in negative x and I get out negative y, or the opposite of y. And again, sometimes that's called odd, an odd function. All right, and so what we want to do is see if this function has any of those properties. So we put in negative x, and we would get 3 times negative x squared over negative x squared plus 1. And in fact, that gives us our original function back. When we square the negative x, we just get the same x back. So we get 3x squared over x squared plus 1. And so this function has y-axis symmetry. Ooh, symmetry. Let's just stop with the M, the double M. Okay, so again, that doesn't give us any information about where the points go, but at least we know that when we try points like 1, 2, 3, that on the negative version they'll be exactly the same. So let's just pick a couple points here. So we've got x and f of x, and I'm just going to go with 0, 1, 3, 5. Right, and if I put in 0, I already know I get 0. If I put in 1, I'm going to get 3/2, or 1.5. If I put in 3, I'm going to get 27 over 10, which is 2.7. And if I put in 5, I'm going to get, let's see, 75 over 26, which is approximately 2.88. right? And again, if I do -1, I'm going to get 3 halves, -3, 2.7, -5, 2.88. So let's just plot that right here. So at 0, it's 0. At 1, it's 3 halves, so 1.5. At 3, it's 2.7. So again, that's about 2 3/4. So we can put that there. At 5, we get 2.88. So we're getting much closer to that level of 3 there. And then let's just do the same thing on the other side. All right, at -2, we get, or sorry, at -3, 2.7, -5, 2.88. And again, we could talk about how we're going to connect them. Is this going to look like this when we connect it? Sharp turn here, or is it going to be a more gradual turn right here as we go down? Because we can see this part is coming in, we can see this part is coming in. But the question is, how do we draw this part? Well, we can look at the differentiability and wonder, is it ever going to make the denominator 0? That would be one way. The other way would be if we had an absolute value, but that's neither of those is going to happen. So it can't be this sharp turn right here. It's got to be a nice rounded curve. Okay, so then let's continue on here, because what we can see is that it just keeps getting, it looks like it's getting closer and closer to this line y equals 3, right? And so it does. We're going to verify that in just a second. All right, but I'm going to draw a horizontal asymptote right here to indicate that it's going to get closer and closer to that value of 3, but not achieve it. So let's just say it looks like it gets closer to 3 as x increases, but let's just verify that. So if you have your calculator, then you can just plug in that function. So I have it already in there. And then when we graph it, right, I have it set for -10 to 10. And so if we do these values, actually we already know at 1 and -1, it's going to be 3 halves. At 0, it's 0. At 1, it's 3 halves. So if we put in 10, so I'm going to say trace, oops, sorry, second trace value, and I'm going to put in 10 and enter, and we get 2.97. So we can put that value in here. Right, if you want to do this with the 100, you're going to have to change your window because your calculator won't let you do it if it's not already in your window. So -100 to 100. All right, let me get out of that again, and then we'll do second trace value. Now if we do 100, whoops, let's do graph first. All right, so if we do 100, we end up getting 2.9997, and again, same thing over here, 2.9997. And so then as x approaches infinity, we can see this just keeps getting closer and closer to 3, right? And so we would say that the limit approaches 3, and here's how we would write it. We would write the limit as x approaches infinity of f of x is 3. That's this direction, and then we could say the same thing in the opposite direction. Limit as x approaches -infinity of the function is equal to 3. Right, and again, we see that from our graph here, that it looks like it approaches 3. We've just made this table to confirm that it approaches 3. So we feel confident that we can say these two things, that as x approaches positive infinity, it approaches 3, and as it approaches negative infinity, it approaches 3. All right, so what the heck does that mean? From a more, again, remember we said when we talked about limits, the formal definition of a limit, what exactly does that mean that it is approaching 3? All right, so what we can say here is, let's imagine that we have some function. Again, I'm just going to draw the graph as it approaches positive infinity, and then you can imagine what it looks like when you go to negative infinity. So let's say I have some function, and I say that the limit as x approaches infinity is L. Right, again, the limit is the y value, so I'm going to put L right here. And again, what that means is that there is, for any epsilon that you can pick, right, there is some m, and again, epsilon really small, and it's going to be something that goes around here. How close do I want to get to that limit? So again, this is a little epsilon window around L. So this is L plus epsilon and L minus epsilon, so just a little window around it. And it's saying, if you say that I can get really close to L, then there is some m, again, m is an x value, before we used to use c, but we're going to say there is some m value where the function just starts settling down. So let me actually draw our graph here. And again, this is just one I've made up here. So let's say the function does like this, and it gets like down here, and then it starts to just kind of do something and just level out, right? And so we're going to say, like, let's say that this is the point M, and this is f of m, right? Doesn't really matter. It's just this is the point that we're looking for. At some point after m, that it's always going to stay in this little bubble around L, right? Or this little window. So it can go and do crazy things before that, but once it hits this value m, it's never going to leave that window. Right, so that's what we mean, that if I pick any value epsilon, small as I want to go, again, maybe you're saying 0.05, but then I say, no, I want to be more tight than that. I pick 0.001. It doesn't matter. Whatever small epsilon I pick, I can find some m somewhere where the function after that just stays trapped in that window. And again, depending on the value of epsilon, that value of m is going to change. So if you pick 0.05, maybe m is here, but if I want to get more stringent, a tighter thing, then my m might have to be out here, right? So, but it's guaranteeing that there is some m such that the distance between the function and L is less than epsilon whenever we get past that value of m. All right, so again, hopefully that looks somewhat familiar to you based on our formal definition of limits as x approaches some constant c, but here's what it would look like for an infinite, that we're heading out towards infinity. All right? Okay, next page. Okay, so then we would say that the line y equals L is a horizontal asymptote. Again, I know you've talked about this before, but y equals L is a horizontal asymptote of the graph if the limit as x approaches negative infinity is L, or the limit as x approaches positive infinity is L. And again, if we look back at this picture right here, this is the line y equals 3. All right, and what we would say is that as x approaches infinity, the graph approaches this line y equals 3, right? And so that's what we would call a horizontal asymptote. All right, and then just as we would hope limits at infinity have the same properties that finite limits do in a lot of cases. So, for example, if we have two functions f and g, and as they approach infinity, they both have limits that exist, then if I find the limit of their sum, then it's the same as the sum of their limits, right? And then again, if I have two functions whose limits exist as they approach infinity, and I have the product of that, I have the limit of the products, then it's the same as the product of the limits, right? And we could say the same thing as we're approaching negative infinity. Okay, so again, as we talked about in original limits, we have to have some sort of starting base here. And so here is our first just kind of building block. We're going to work from that and build our way up so that we can find limits at infinity of lots of rational functions. So first we have is r, if r is a positive rational number, right? So here's our r. So we've got some exponent and it's positive and it's rational. So no pi, no square root of 2 up there. We've got to have something like, 5 or 1/2 or something positive and rational. And c is any real number. So we've just got some sort of constant up there. Then the limit as x approaches infinity of c over x to the r is going to be 0. And again, hopefully that's not too earth-shattering. If we think about functions that we know like this, like let's say 1 over x, again, in this case, c would be 1 and r would be 1. We know what this looks like, right? It's just a graph that looks like this. Has a vertical asymptote at 0, and it's going to look like this. All right. Well, as x is approaching infinity, this denominator is getting bigger and bigger and bigger, and that means that the overall fraction is getting smaller and smaller and smaller. That's exactly what's happening here. For small values of x, like 1/10, this is going to be big. 1/10, 1 over 1/10 becomes 10. But as we let x get bigger and bigger and bigger, the whole fraction gets smaller and smaller and smaller. And it's going to approach 0. It will never, on this side, become negative because our x value is always positive. All right? Okay, so furthermore, so again, we said that r is a positive rational number and c is any real number, that we can say as x approaches in positive infinity, that it's this. If x is defined, if x to the r power is defined when x is less than 0, then we can also say this is true as x approaches negative infinity. So think about if we have 1 over x to the 1/2, that would be a problem because we can't put negative numbers in the radical. So it's trying to eliminate us doing something like this. It's always safe to take the limit as x approaches positive infinity, but as it approaches negative infinity, we need to be careful about whether we're going to go outside of the function's domain. All right, so just pay attention to that. Make sure that you're not doing something that's going to make the denominator, that it would be outside its domain. Okay, so let's see how we can use that then to find the limit of something that's not just plain like this. All right, so we're going to look at this function, and then we would say, okay, according to this up here, that says that if I have a sum, again, that could be a difference too, of two functions whose limits exist at infinity, then I can just break it apart into finding the limit of each piece. All right, so I'm going to do that here, and I'm going to say that the limit of this difference right here, right, is the same as finding the limit of each piece, but subtracting those limits. So then this is the limit as x approaches infinity of 5 and limit as x approaches infinity of 2 over x squared. All right, and this is just the properties of limits that we talked about up above there. Okay, so then let's take a look at this. The limit as x approaches infinity of 5, again, this is just the constant function y equals 5. All right, so as x approaches infinity, this is just going to stay a constant 5. All right, now let's look at this. So that's going to be minus in here. This is now saying, okay, we're in this situation that we had right here. This is our c value. Right, it's 2, and this is our r value that we're talking about. And again, that is a positive rational number. Right, so it's telling us, this theorem 3.10 says that as x approaches infinity, this is going to go to 0. Right, so again, this comes from theorem 3.10. Right, so then we would just say, well, then the limit is 5. So as this function goes to infinity, it's going to, the y value is going to approach 5. Okay, let's look at the next page. Okay, so then let's look at another example. So here we don't have what we had in theorem 3.10. Again, theorem 3.10 says the limit as x approaches infinity of c over x to the r is 0 as long as r is positive and rational. So let's see what this is going to do for us, because now we have to kind of think about what might happen here. So if we just say, all right, well, we also know this, limit as x approaches infinity of f of x times g of x is the same as limit as x approaches infinity of f of x over limit, oops, kidding, sorry, I was thinking what I wanted to do with this one, times the limit as x approaches infinity of g of x. Let's see if it works to do, well, it will, because g could be 1 over x to the 1 over x plus 1, and f is, so let's just write that down just so you see where I'm going with this. Let's let f of x equals 2x minus 1, and g of x be 1 over x plus 1. And then we can say, oh, okay, now I can use this right here. So this, but I'm just going to look at it like this. Limit as x approaches infinity of 2x minus 1 over limit as x approaches infinity of x plus 1. Right, so as x approaches infinity, this, well, x is just going to keep getting bigger and bigger and bigger. Then I'm going to double something really big and subtract 1 from it. That 1 is a joke. It's not going to do anything. So really we're just looking at this. This is linear and it heads towards positive infinity as we go to infinity. So this is going to go to infinity. Same thing here. Linear, it's got a slope of 1 as x approaches infinity. This is also approaching infinity. All right, and so what happens is we get this form infinity over infinity, which is going to be our second indeterminate form. So this results in the indeterminate form infinity over infinity. If you remember when we were doing limits earlier, we ran into 0 over 0. And what 0 over 0 meant when we were talking about limits as x approached some finite number c is that if we got that, it meant that c was a 0 of both of them. It was a common factor. And so we had to rework it. Just indicated that something else was happening and we needed to investigate. And what that thing was is that it was going to result in a finite number. That the limit was not, we were not going to say limit doesn't exist. And same thing here, this indeterminate form means we just need to do some more investigation. Something is happening here, but we don't quite know what. Okay, so then let's try something else, because doing this didn't work. It gave us an indeterminate form. So I'm going to do this. I'm going to say, take my original function, and again, this is the only building block I have to use. All right, so I'm going to try and make it so that we end up rewriting this in a way that has an x in the denominator. All right, so what I'm going to do is I'm going to take and I'm going to multiply top and bottom by 1 over x. All right, so I'm going to bring this in and multiply that by 1 over x, and I'm going to multiply the denominator by 1 over x. And so what's going to happen is I'm going to end up with 2x over x minus 1 over x, and then in the bottom, x over x plus 1 over x. If I just distribute that 1 over x into each term. Okay. And then we're going to have limit as x approaches infinity. If we simplify this, we end up getting 2 minus 1 over x, and then 1 plus 1 over x. All right, now it's just two baby versions of the problem that we just did. Example 1, remember where we had 5 minus, what was that? 2 over x squared. We're in that same form here, both numerator and denominator. So as I let x go to infinity, this is going to go to 0, and this is going to stay going to 2. So we're going to have 2 minus 0. All right, and then in the denominator, again, that's just the constant function 1, so that's going to stay 1, and this is going to go to 0. And so we will end up with this function approaching 2 as x approaches infinity. All right, so let's take a look at that, and then I want to go back and revisit just why we're allowed to do that, because you might be concerned about the fact that sometimes that function 1 over x is undefined. So let's just go here and draw what our function looks like. All right, so at -1, it's going to have a vertical asymptote. And then it's telling us that as x approaches infinity, it's going to approach +2. Right, and we could just try a couple values in here to see whether this is going to stay only down here or it's going to go up here. Actually, we could see that the numerator is 0 when x is 1/2. So at 1/2, it's going to cross right here. Well, that means that it's got to go like this. Sorry, that wasn't very nicely drawn. Something like that. Oh, that's because I'm... Let's try that again. Okay, that looks a little bit better. And then if we put in something like -2, that -2, that's -4 minus 1 is -5, over -2 plus 1 would be -1. So -5 over -1, which means we're going to end up somewhere up here, which means that the graph is going to look something like this. All right, so we would say the graph has a horizontal asymptote. At y equals 2, to the right, or as we approach positive infinity. And then you could do the whole process again as x approaches negative infinity, and you'll see that it's the same thing. All right, that it's also going to approach +2 as x approaches negative infinity. All right, but before we move on from this, I just want to address the question that you might be having, which is, well, why am I allowed to multiply by 1 over x? Because I would have to consider what happens, like if this becomes undefined. All right, because again, 1 over x is undefined when x is 0. We just had that graph drawn a second ago. So as x approaches 0, yes, we have a problem, all right, because there's a vertical asymptote right there. But again, remember what we're doing here. We're not getting anywhere close to 0 because we're asking what happens as x is approaching infinity. So yes, if we were trying to approach 0, then I would be really concerned about doing this. But the fact that x is approaching infinity and we're nowhere near that problem spot says, oh, I'm never going to run into a problem here because as x approaches infinity, this is always defined. Right? And so 1 over x over 1 over x will always be 1. It's not going to do something weird here because, well, it will do something weird here, but we're not concerned about that because we're not anywhere near it. All right? Okay, so then let's try 3 other functions. Again, you might be thinking, gosh, this is kind of a pain in the neck to do that. Is there a shorter way? And yes, but first we're going to take the long way to get to the short way. So again, I have 3 different functions here. All look very similar. There's a 2x plus 5, 3x squared plus 1. Here, the denominator stays the same, but the numerator gets an x to the second. And then here, again, the denominator stays the same, but now we have an x to the third. And we're going to see that in each of these, we have something different happen. And that's going to help us come up with some rules about how we can just look at a rational function and say what the limit is as x is approaching infinity. Take a look at the first one. And again, if you remember that we've got theorem 3.10, this one up here. And so we don't have anything that looks like that right now. We have no x's in the denominator of a single fraction. All right, so let's see if we can try to make it look that way, and using what we just did again up in the previous problem. So here I'm going to do the same thing I did before, except I'm going to choose to multiply not by 1 over x, but 1 over x squared. 1 over x squared. All right, again, the reason I'm choosing x squared is because I need something in the denominator here that's going to have a 1 over x in it, but I don't want this to have an x still because then that's going to go to infinity. So I want to have enough to get rid of that. Right, so then this is going to be the limit as x approaches infinity. When I distribute that in, I'm going to get 2x over x squared plus 5 over x squared over 3x squared over x squared plus 1 over x squared. All right, limit as x approaches infinity. This is just going to become a 2 over x. Sorry, I meant to write that. Yeah, 2 over x plus 5 over x squared over, this will just become a 3 plus 1 over x squared. Right? As we let x go to infinity, we know by theorem 3.10 this goes to 0. This goes to 0. This is just a constant that's going to stay at 3. And this is also going to go to 0. So we end up with 0 over 3, which is 0. Right? So as x approaches infinity, this whole function goes to 0. All right, part B. All right, again, I want there to be a 1 in the x in the denominator, or a 1 over x in the denominator somewhere. So x squared multiplied by 1 over x squared should work again here. So as I do that, limit as x approaches infinity of 2x squared over x squared plus 5 over x squared. This is 3x squared over x squared plus 1 over x squared. Right, this simplifies to 2. And this simplifies to 5 over x squared. Down here, this simplifies to 3, and this simplifies to 1 over x squared. They're both simplified already there. Okay, so as x is approaching infinity, again, that's a constant. It stays at 2. This goes to 0 because of theorem 3.10. This is a constant. It stays at 3. This goes to 0. And so we end up with 2/3. All right, so our first function went to 0. Our second function, as x approaches infinity, is going to go to 2/3. All right, part C. Limit as x approaches infinity. Again, let's do 1 over x squared. And I'll show you what happens if we try something else here that wouldn't quite work, but let's stick with 1 over x squared here. And so in the numerator, we would get 2x cubed times 1 over x squared is just, well, 2x cubed over x squared plus 5 over x squared over 3x squared over x squared plus 1 over x squared. This, the x's will partially cancel out. We'll be left with 2x. Sorry, I forgot my limit here. This is 2x plus 5 over x squared. And in the denominator, we get 3 plus 1 over x squared. Right. All of this is very similar to what we had before, or identical. So this part is going to go to 0. This is going to go to 3. And this is going to go to 0. This, however, again, this is just a linear function right there. It's going to go off to infinity as x approaches infinity. So this gives us infinity. Infinity plus 0 is infinity. Infinity divided by 3 is still infinite. Right? And so this one will go off to infinity. Let me just point out that maybe you're thinking that we should always go with the highest exponent. So here the higher between the two was the x squared. Here there was no higher, they were both x squared. Here it's x cubed. So let's just pause for a second and see what would happen if we chose 1 over x cubed. Just to show that we do need to give some thought about to the x, the power of x that we're using right here. So I'm just going to do this off on the side here. So if I chose, instead of this, if I chose 1 over x cubed, right, you don't have to write this, I just want, you can, but just realize this is the correct answer. this is going to give us a problem here. So if I put multiply by 1 over x cubed, and again, I'm tight on space, so I'm just going to multiply and cancel at the same time. When I distribute this, it's going to give us a 2 plus 5 over x cubed. And in the bottom, it's going to give us a 3 over x plus 1 over x cubed. Right, this is fine. This just gives us 2 plus 0, which is going to give us 2. But in the bottom, this is going to go to 0, and this is going to go to 0, which would mean the whole thing would go to 0, which is going to give us 2 over 0, which just doesn't help but answer the question. Right, so if you get something like this, specifically where you get a 0 in the denominator, you've probably multiplied by a power of x that's too high. So I would say you definitely don't want to make that become a fraction right there. It's going to be this one that you want to be the fraction. All right, so don't overdo it by picking the highest one. Pick the one that's going to take care of that. All right, that will make that a constant and this a fraction. Okay, so then think about that for just a second. This went to infinity. This went to 2/3, and this went to 0. So just changing that power of x in the numerator caused each of these to have a different thing that it approached as x approached infinity. So here we would say their horizontal asymptote was at 0. Here it is at 2/3, and here it's at infinity. All right, so let me bring in this list here, the guidelines that we're going to talk about. I don't think you'll be able to see both of these at once, so I might have to move things around. But if the degree of the numerator is less than the degree of the denominator, then the limit of the function is 0. So look what we had here. The degree of the numerator is 1, and it's less than the degree of the denominator, 2. And it says when that happened, the function goes to 0. All right, so let's think about why that would happen. So as x is going to infinity, this is getting huge, and this is just staying at constant 5. This is really adding next to nothing as we start getting really large values of x. So this is just kind of a nothing as x goes to infinity. Likewise, that 3x squared is not impacted substantially by adding 1 to it. So we can say as x approaches infinity, these two constants really do almost next to nothing. And so really, as x gets farther and farther away, we're looking at 2x over 3x squared. And again, this would reduce to become 2 over 3x. And then we can say, yeah, this is, as x goes to infinity, this whole fraction is going to go to 0. All right, so again, just by kind of ignoring those parts that really are not as impactful as this, as x goes to infinity, we see that essentially we're looking at this function, and we would see how this numerator is not going to keep pace with this denominator. Or we could say we could cancel out those x's, and then that is the only thing that's growing, and this is staying constant, roughly. Okay, if the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of the leading coefficients. That's exactly what happened here. So here, the numerator and the denominator had the same degree. And as x approaches infinity, again, this plus 5 is not doing a whole lot. This plus 1 is not doing a whole lot. And so really we're just looking at what happens to this as x approaches infinity. So this is 2x squared over 3x squared. And these will just cancel out and leave us with that 2/3 that we got. All right, so again, we're just disregarding the parts that really are not making an impact. They're there, but as x gets close to infinity, it's laughing at plus 1, thinking that's going to make any difference. It's really this guy that's carrying all of the weight, and this plus 1 is just kind of a nothing. All right, and then finally, if the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function does not exist. It's going to go to either positive infinity or negative infinity, and that's exactly what we saw here. Again, this is not doing anything, so we're really looking at this, 2x cubed over 3x squared. And again, as we cancel some of these x's, we end up with 2x over 3. And this, again, becomes linear, and it goes off to infinity. All right, and so we would say the degree, if the numerator is higher than the denominator, then it doesn't exist. All right, but we have a special note here. If the degree of the numerator is exactly 1 degree greater than the degree of the denominator, then the rational function, sorry, that's a typo, the rational function has a slant asymptote, which is a linear equation. All right, so let's pause for a second. That's exactly what's going on here, that this is 1 degree higher than the denominator. And we said when we ignore those really non-essential parts, what we end up with is a linear function. Right? So if it's exactly 1 degree higher, it's going to go to infinity, but in a linear way. Right? If it were 2 degrees higher, then it would go to infinity in a quadratic way. We don't necessarily pay attention to that, but if it's linear, then we can say, well, that's helpful. I know what that's going to look like, and we'll start to take into account how it goes off to infinity, right? The equation of the slant asymptote can be found by dividing the numerator by the denominator, either using long division if the degree of the denominator is greater than 1, or synthetic division if the degree of the denominator equals 1. Right, so we're going to see on the next page, or 2 pages from now, that we'll look at an example of that. But for right now, let's take a look at it. Example 4, a function that has 2 horizontal asymptotes. All right, one as it goes towards positive infinity and one as it goes towards negative infinity. So this most often happens when we have a square root function. So let's take a look at what goes on here. All right, so I'm going to do it in 2 separate parts. All right, so as we look at this one, again, we need to make that fraction the c over x to the n somehow so that we can get that part to go to 0. But it's a little bit trickier when we have square roots in it. So we're going to take note of something that happens with square roots, and we're going to say since x is approaching positive infinity, we have x greater than 0. And then when we take the square root of an x squared, again, that's what we have more than that, but essentially if I have an x squared, when I do the square root of a positive number squared, so let's say we did 5 squared and we took the square root of it, we would get 5 right back. Right, that's going to be a little bit different here when we go to the negative side, but for right here we can say the square root of x squared is just x. I get back exactly what I put in when x is greater than 0. So since we're going to infinity, positive infinity, we know x is greater than 0, and we can say, hey, when x is greater than 0, the square root of x squared is x. Right, so we're going to use that fact, and in the numerator, we're going to multiply by 1 over x, and in the denominator, we're going to multiply by 1 over square root of x squared. Right, again, because this is the same as x, so again, this is still a 1. We've just written it as a different version of that, but an equal version of that. Right, so the numerator, this is going to become 3 minus 2 over x. And then in the denominator, let me write it out and not simplify it just yet. 2x squared plus 1 over square root of x squared. Right, again, if you want to write that out with this, I'm just going to cancel that just so we save a little bit of space here. Okay, so then the next thing I'm going to do with this is I'm going to put it under the denominator, or under the radical here. Because remember, when we have 2 radicals, then we can just smush that together into a single one. So in the numerator, we've got that 3 minus 2 over x. And in the denominator, this is going to become the square root of, this will, let me just do it in another step here, 2x squared over x squared plus 1 over x squared. Then this is going to become limit as x approaches infinity of 3 minus 2 over x over, this is just going to become a 2, and this is going to become a 1 over x squared. Right, so as we let x go to infinity, then this stays 3, this becomes 0, this is going to become 0, and this is going to stay a 2 under the radical, and therefore we end up with square root of 2 plus 0, which is going to give us 3 over root 2, which is approximately 2.12. All right. Again, it's this idea that when x is positive, x and square root of x squared are identical, and then that's how we can do what we just did. All right, not so much on this side. Now, since x is going to negative infinity, we have x less than 0. And when x is less than 0, so again, over here we did positive 5. Let's suppose I take the square root of negative 5 squared. Well, order of operations says do what's in the under the radical here, and we would do the exponent, so we would get 25, but when it comes out, it's positive 5. All right, square root of 25, we always assume the positive version unless it has a sign in front of us to tell otherwise. So here we get a positive 5 out, which is the opposite of what we plugged in. All right, so as x is approaching negative infinity, in other words, when x is less than 0, the square root of x squared is not equal to x, it's equal to the opposite of x. All right, so whatever I put in there, I'm going to get the opposite out. Again, if I put in a negative number, the opposite of a negative number is going to be positive, but it's still the opposite of what I put in. All right, so then let's do the same thing here, except this time we're going to multiply top and bottom by 1 over negative x and 1 over x squared. Or sorry, 1 over square root of x squared, because we know that square root of x squared is equal to negative x, and so I want to make sure I'm multiplying top and bottom by the same thing. All right, and again, I'm not going to choose to make this negative because then I'm going to bring a negative under the radical there. So we're just going to do 1 over x squared, or 1 over square root of x squared is 1 over negative x. Okay, so that is going to look like this. Limit as x approaches negative infinity of 3x over negative x minus 2 over negative x. And then down here we're going to have square root of 2x squared plus 1 over square root of x squared. All right, here this is going to become negative 3. This is going to become plus 2 over x. And when I put this under the radical, this is going to become 2x squared over x squared plus 1 over x squared. Next step has us still the same in the numerator. That's negative 3 plus 2 over x. But down here, we're going to get square root of 2 plus 1 over x squared. All right, so just like we did over here, this is going to end up giving us negative 3 plus 0, and then this is going to give us a square root of 2 plus 0, which is going to give us negative 3 over root 2, which is approximately, oops. All right, sorry, I think I just got caught off right here. So what I was saying is as x goes to negative infinity, sorry, I forgot that negative there, forgot it there. As it goes to negative infinity, we get this, which ends up giving us negative 3 over root 2. So negative 2.12, opposite of what we got here. So let's just do a sketch of what this looks like. So we're up at 2, we're down at negative 2. And so just a hair below negative 2, we've got our horizontal asymptote. Well, that's more than a hair. All right, and just above positive 2, we've got our horizontal asymptote. And so the graph comes in like this, and then it does some little weird jig here, and at negative 2 it's 0. At 1, sorry, let me get this a little bit more accurate. At 1, it crosses over the x-axis here. And then it goes up at 2, it's maybe right about here. And then it goes off like that. All right, so that's what a function would look like if it has 2 horizontal asymptotes. And again, It usually happens when we've got a square root because of that positive negative thing where square root of a negative number squared gives you the opposite of what you put in. Square root of a positive number squared gives you exactly back what you put in. Okay. You can't ever do these without looking at the trig part of it. And so let's take a look at these two functions right here. So the first one is, well, they're both familiar to us, but for different reasons. This is sine, just a nice, lovely function, defined everywhere. All right, continuous everywhere, differentiable everywhere. All right, and so it's asking as x approaches infinity, what happens to the sine function? Right? If you think about what we said right at the beginning about what it means to have some sort of limit at infinity, it means that after a certain point, the function just kind of calms down and starts behaving like a linear, a just horizontal line, right? And so hopefully it's easy to see here that that's never going to happen with sine. It always is oscillating back and forth between -1 and 1. So here we would say as x approaches infinity, the sine function oscillates between -1 and 1. So this limit does not exist. Again, we could change that to negative infinity and it would be the same thing. It's still going to have that same pattern of going between -1 and 1. Sorry, this is supposed to say sine. Okay, now we've also seen this. This is just a limit that we knew as x approached 0 of sine of x over x. We said that was going to be 1. All right, but now that's not asking us that. It's asking us what goes on as x approaches infinity or negative infinity. All right, so let's first note that this function, actually this function right here is always between 1 and -1. So we can say that sine is always between 1 and -1. All right, so then it follows that for x greater than 0, again, not equal to 0, not less than 0, but greater than 0, that -1 over x is less than or equal to sine x over x, which is less than or equal to 1 over x. Right, again, it can't be less than 0 because then that changes the direction of the inequality. It can't be 0 because then these would all be undefined. Right, so if it's strictly greater than 0, then we're allowed to divide by x, and that inequality, the direction of the inequality stays the same. All right, we know that the limit as x approaches negative infinity of 1 over x is 0, and sorry, I think the limit was, I think this is supposed to be the limit as x approaches infinity of 1 over x is going to be 0, and the limit as x approaches infinity of 1 over x. I said it and then I still wrote it wrong. Right, the limit as x approaches infinity of -1 over x is 0. The limit as x approaches infinity of +1 over x is approaching 0. So we can say by the squeeze theorem, again, that's like a blast from the past, by the squeeze theorem, then this limit as x approaches infinity of sine x over x must also be 0. Again, squeeze theorem said if I can take some function and trap it between two other functions that approach some value, some constant number, in this case it's going to be 0, but if I can get those two functions to trap this one that we're looking at in between those two, If these are both pushing towards 0, again, these are bounded. This is always going to be, sine of x over x is always going to be less than 1 over x and greater than negative 1 over x. It's trapped between these two. So as these two functions, the 1 over x and negative 1 over x, are coming towards 0, it squeezes this between it, and so it must also stay with a limit going to 0. Right? So again, this is going to become 0, whereas when it went to a finite 0, it became 1. When it goes to an infinite, it becomes 0. All right, word problem. So we have, suppose that f of t measures the level of oxygen in a pond, and its normal unpolluted level is 1. Whatever unit of measurement we're doing here, it's 1. And time t is measured in weeks. All right, when time is 0, t is 0, some sort of organic waste is dumped into the pond. Right, so that could just be leaves, the grasses, something is going in there that's organic. Most times it would probably be leaves. I had to look this up to see why it was bad that this happened, but then it causes stuff to go in there, which then to decompose sucks out the oxygen, and then fish in the pond will start to die. Right, so organic waste is dumped in there, so maybe leaves are falling in as the trees are dropping them, and the waste material oxidizes, and then the level of the oxygen in the pond is going to change. And so that level of oxygen is modeled by this equation right here, t squared minus t plus 1 over t squared plus 1. So it's asking us what percent of the normal level of oxygen exists in the pond after 1 week, after 2 weeks, and after 10 weeks. And as the limit approaches infinity, what happens to t then? Or as t is approaching infinity, what happens to the function then? So let's just take a look at what's going on here, because it's asking us first, what's the percent of this? All right, so f of 1. So we plug in 1 here, we get 1 squared minus 1 plus 1 over 1 squared plus 1. And that ends up giving us, these cancel out, so we get 1 over 2. And so it's at 50% of what it was originally. So if normal was 1, it's now at 50% of that. All right, it's also asking us now to do after 2 weeks. So f of 2 is going to be 2 squared minus 2 plus 1 over 2 squared plus 1. It's going to give us 4 minus 2 is 2 plus 1 is 3. And here we're going to get 4 plus 1 is 5. So that is 6/10, which is the same thing as 60%. All right, so it dropped from its normal of 1 and that to 50%, and now after 2 weeks it's climbing back up a little bit. So we're back at 60%. At 10 weeks, we will put. Okay, my SD card just got full, so let me just repeat this because I'm not sure if it cut this off. But to find out what the percent of the normal oxygen level exists in the pond after 1 week, we're going to do f of 1. Right, so we plug 1 into the function. 1 squared minus 1 plus 1, 1 squared plus 1 gives us 1/2, or 50% is still left, or exists. Only 50% of the normal is left. Right. F of 2 is going to signify after 2 weeks, 2 squared minus 2 plus 1, 2 squared plus 1, we get 3/5, which is 6/10, which is 60%. And then when we're 10 weeks out from when that waste material was dumped in there, dropped in there, we get 10 squared minus 10 plus 1 over 10 squared plus 1. That's 100 minus 10 is 90 plus 1 is 91. And then we're at 101 in the denominator, which is roughly 90.1%. All right, so even after this material is dumped in, it will start to return to normal. Right, and so what this looks like is, let's see, 2, 4, 6, 8, 10. And then here, I'm going to mark these bigger since we're talking about percentages. Let's do that as 1.0, and then this would be about 0.5, 0.25, and then 0.75. All right, and normal is up here at 1. And so what happens is it starts at time 0, it's normal, but then it's going to drop down, and after 1 week it's dropped down to 50% of normal. And at 2 weeks it's bounced up a little bit, it's up at 60%, so maybe somewhere right around here. And then when we're out at 10 weeks, it's almost back up to normal, it's up at 90%. All right, so the function is going to look something like this. Probably not that part. All right, and then it's going to come up like this and level out again. So just roughly like that. All right, so it's asked us these several questions here. After 1 week, done. After 2 weeks, done. After 10 weeks, done. But now it's asking what is the limit as t approaches infinity. So we're going to take our function, the limit, as x approaches infinity, t approaches infinity, of t squared minus t plus 1 over t squared plus 1. And again, we could do this 2 ways. One is we could do the multiply everything by 1 over t squared like we did before. All right, so we would do that to the top, do that to the bottom, and we would end up with limit as t approaches infinity of, distribute that, we get 1 minus 1 over t plus 1 over t squared over 1 plus 1 over t squared, and then that would show us it goes to 1. Or we could use our new trick, which was we look at the highest power in the numerator and the denominator, and if they are equal, then it's just going to be the ratio of the coefficients. Well, the coefficient of both t squareds is just 1, so the ratio would be 1 over 1, which would give us 1. So either way, whether we do our dividing out to get that form c over x to the n, whoops, not to the second, c over x to the r, or if we use our guidelines for finding limits of rational functions, either way we end up getting 1. And so then after an infinite amount of time, or as t gets bigger and bigger, it's going to go back to its 100% level of 1, which is normal. So it's not this one per se, it's 1 meaning 100%. Okay, last page. Definitions of limits at infinity. Let f be a function defined on the interval a to infinity. The statement limit as x approaches infinity of f of x is infinite means that for each positive number m, there's a corresponding number n such that f of x is bigger than m whenever x is bigger than n. This is definitely going to maybe require a picture here. So it's saying if we say that the limit is infinite, then remember, m is like our c value when we were talking about finite's limit. So for any positive integer m, there is some integer n, sorry, got those backwards. All right, so that for every positive integer m, there is some number n such that when x gets beyond this point n, the function is going to cross this line. So we might be thinking, oh, this looks good, it's fine, it's staying below this number m, but it's saying no, at some point it's got to cross over m right here, right? So it's saying it might be below m for a while, but there's if the limit is infinite, then no matter how far I go up, how far I try to reach to say, well, maybe it just won't pass this line, that we're going to say no. If the limit is infinite, then we're going to say I can always find a number n such that after some point the graph is always above that. All right, so I just can't possibly find some way to bound my function up above, that every time I try, every m value I pick, that I can find an n where it goes higher than that. Right? So this is for as x goes to positive infinity. Right? We could say the same thing that, either way, it says x goes to positive infinity, but if we say that the limit is positive infinity, this is what it looks like. If we say that the limit is negative infinity, all right, then we would have a very similar picture here. All right, that x is going to be greater than n. I don't know why I drew it that way. So same kind of thing like this. All right, so if I say that there is some negative number m where I'm positive that this is just, the function's not going to go below that, I say, I think I can do it. I think I can block it by there, and it's saying, no, if the limit is negative infinity, then at some point there will be an n greater than 0, such that when n exceeds that, the function goes below the value that I tried to block it with, right? So again, it could be like, it's fine, it's up here, it's doing its stuff, but at some point it will go below that value that we hoped to block it by, right? So that's what we mean when we say that as x goes to infinity, the function goes to negative infinity, right? We see this with linear equations all the time, right? That we might say, oh, maybe when it gets to 1,000, it's going to stop, but then we could say, no, it's going to continue increasing forever, right? And so we can't block it above by some number m. At some point, it will get above that. All right, and we could say the same thing if we let x go to negative infinity, and the limit is positive infinity, or if we let x go to negative infinity and the limit is negative infinity. All right, so for example, we could say, in these two, again, I said linear, but cubic also works like this. As x approaches positive infinity, so as x increases without bound, x to the third also increases without bound. Again, we know what this looks like, something like that. So as x increases without bound, in other words, as x goes to infinity, this function is also going to go to infinity. So we would say, so limit as x approaches infinity of x cubed is infinity. All right, in this one, we're letting x go to negative infinity. We're keeping the same function here. Right, so again, as we plug in negative values, like -2, we're going to get -8. We plug in -3, we're going to get -27. We plug in -4, we get -64, and so forth. It's going to keep getting lower and lower and lower. So as x decreases without bound, x to the third also decreases without bound. So the limit as x approaches negative infinity of x cubed is negative infinity. Right, again, we see that right here in this picture. Okay, so it's asking us to find limits at infinity, and notice it's exactly the same problem. That's not a mistake. We have two different ways that we know how to do, or actually we have a way that we know how to do this. We could, we could just, actually we have two different ways that we can do this. The first is the shortcut, which is we can just compare these and say, oh, since this is higher, the power there is higher than the power here, this is going to go off to infinity. Right, that's one way, our shortcut. Our second way is to do it with the multiplying by 1 over x's. So if I just do limit as x approaches negative, oh, sorry, they're not the same function. All right, let's just do this one as infinity, and then I'll do this one the other way that we're talking about. So as x approaches infinity, if we multiply top and bottom by 1 over x, again, we saw in that previous example, we don't want this to have also have an x in the denominator. We only want one of them to have an x in the denominator. So we're going to choose the power of that x in the denominator, which is just to the first. So this ends up becoming 2 over x minus 4, right, distributing those through. And then in the denominator, it's going to be 1 minus 1 over x. Right, as x goes to infinity, this goes to 0. And as x goes to, oh, sorry, I made a mistake there. This shouldn't be 2 over x. It should just be 2x. As x goes to infinity, this goes to infinity, minus 4. This goes to 1, and this goes to 0. All right, so that's another way that we can see this goes to infinity. All right, so again, you're just always going to end up using the shortcut, which is fine. If you get into a sticky situation, I don't want you to forget how to do this right here. All right, but let's do this problem again, now this time with negative infinity. And I want to use the fact that, remember, back on the previous page, we said that if we get 1 power higher in the numerator than the denominator, this is actually going to grow to infinity, but in a linear way. And so we said we could either do this by long division, or we can do it with synthetic division. So let me show you how to do it with synthetic division. And so we're going to set this up. Remember along the top that we put each of the coefficients, so that's a 2, a negative 4, and a 0 for the constant term. And then over here we're going to put the opposite of whatever that is. So that's a positive 1, we're going to write negative 1. Right, we bring that 2 down, this becomes negative 2. This becomes negative 6. We put the negative 6 up here, and we end up with negative 6. All right, so what you might remember from synthetic division is that when we get something other than 0 in there, that means the x plus 1 does not divide into this evenly. But the other thing it tells us is that this is the quotient. The 2 and the negative 6 right there end up being the quotient, and this negative 6 ends up being the remainder. What I mean by that, remember, this is the constant term. This is the remainder. And this is the coefficient of the x. All right, so what this means is that this breaks down into, let me just skip writing the limit for a second. This, when I divide by x plus 1, this becomes the polynomial 2x minus 6 plus, and it's a remainder of negative 6 over the thing that we divided by. All right, so if we do look at the limit then as x approaches infinity of this whole function, this part goes to 0, this part goes to negative 6, and this part goes to infinity. All right, so we see again that it's going to negative infinity, so this goes to negative infinity. So we see again that this goes to infinity, specifically negative infinity at this point. But we can see how it goes to negative infinity, and what we're going to see when we graph ones like this is that it approaches it in a linear kind of way. So let's say this is negative 6, and then again I'm just going to sketch it. So what it's going to say is that, and then we can also draw in, it's got a vertical asymptote here, that it's going to kind of be bound in between these two asymptotes, one slant asymptote and one vertical asymptote. But we'll practice graphing like that in the next section. So for right now, just know that as x approaches negative infinity, the function approaches negative infinity in a linear way, and as it approaches positive infinity, it approaches positive infinity, but also in a linear kind of way. All right, so we'll practice more of that in class, but for right now, just know that if we're trying to see how it approaches infinity, if it's 1 power higher, that's what you could do. Okay, see ya.